Here are the links to the tutorial in Dipy that we will be following, and then a demo data that I have prepared for this tutorial. If you would like to run BUAN with me, go to this link and download the data. And here is the link to the entire dataset generated by BUAN paper. This is how the demo data looks like from the figure, where we have bundles and subject small folder. If you download it, then we can move to the demo. And this is the demo that we will be following. This is the tutorial. So in this tutorial, in the Dipy, we already provide the links to the data, but this is data for 30 bundles. But for now, we'll be just using demo data, which is just for one bundle, that is arcuate fasciculus, and one DTI measured FA. Let's open the terminal now. So all of these commands are available in Dipy. By now you must have downloaded Dipy, and with Dipy you get these workflows command line. If you do Dipy _dept, you can see all the workflows available in Dipy. Great. Now let's start the tutorial. So in BUAN, to perform group comparison on bundles, we have two parts. One is for the bundle profiles and one is for shape similarity. So let's start with bundle profiles. In the bundles that we already have, that we downloaded from the data the data link that I provided, bundles folder normally has the model bundles. It can have as many bundles as you want to analyze, but for now we have just one bundle, arcuate fasciculus, and then the folder subject small. It must have this kind of a structure where we have two groups, in our case control, patient, and then in each group we have subjects. Here we have 5 subjects, and each subject has anatomical measures where you could have FA, MD, RD, and then we have org bundles, which is bundles in original or native space that you get from recobundle, and this is recobundle output that is in common space, so in this case MNI space. So let's see how this data looks like for the demo data. Let's do tree. Here we have total 10 subjects, 5 per group, and in each group we have, as I mentioned, anatomical measures. For now we just have one file, FA, but you can have as many as you want. And if you want to have some other measures, for example CSA, from the CSA, if you want generalized fractional anisotropy, you can give it a CSA peaks spem 5 file. And then we have bundles in native space and bundles in common space. These are generated from recobundle. So now that we have understood the data structure, let's start the tutorial. First we'll need to create a folder where the bundle profiles will be saved. So let's create a folder. Now we can run this command dipy BUAN. If you wish, you could just copy it from here, but I'm going to write it. And the first argument dipy BUAN profiles needs is bundles folder that has the model bundles. And then the second argument it needs is subjects folder. Here the name of my subject folder is subject small, and it has the groups control and patient inside it. And then let's give it the folder where output data will be saved. So it will be the folder that we just created, and this will be as a string. If you don't specify the output folder, it will save your output in the current directory from where you're calling this workflow. So this workflow will create the bundle profiles that we discussed in part 2, where it segments the bundles by default in 100 segments, and then saves the data of which point belongs to which segment and what are the projected measures, in this case FA, and saves it in .h5 file. So while this is running, it will take a minute or two. Let me show you this dataset that is in bundle analytics tutorial, the original one. Here we have data for 30 bundles and whole brain for you, and in this one here, let me show you. I have compiled 3 data sets, so the link is provided, where we have the entire data set that we created for BUAN paper for 64 subjects, 32 patients, and 32 controls. It includes 30 bundles per subject, both in native and common space, and then it has some DTI measures that you could use. And then there is this test sample that has total 10 subjects, 5 patients, 5 controls, and 30 bundles, and the DTI measures. So this is the one. If you would like to run this in your free time, you can run on this one. All the commands will remain the same. You just need to use this data set. And then of course there is the BUAN demo that we are using right now. So let's see what's the progress. It shows you in which subject is being processed right now. So now it's in the patient, and I think we are already done with the control. Yeah, we are done. So let's see what this created. So if we look at the bundle profiles output folder, it has created .h5 file that has the information about the points belonging to which streamline, which subject, which group, what are the FA values over there, which disk it belongs to. Great. Now let's feed it to linear mixed models and do some statistical analysis. Let's create a folder. And now there is this command dipybwan lmm, and what it takes is it input the first folder in which we have the bundle profiles created, and this is it takes it as a string, so you have to give it like that, and the output folder directory. Now this will run linear mixed models per segment. So per segment it will get data from, for segment 1 it will get data from all the subjects and from its arcade fasciculars bundle in this case, and all the points that belong to that with FA projected on it. So it is trying to find any differences between patients and groups. So while it's running, let me show you some more tutorials on BUAN that are available in Dipy. So this is bundle assignment maps. So for example, if you are interested in just creating those segments that I talked about before, let's go and see those here. If you're just interested in creating these segments and you have a bundle, and you have a model centroid, and you just want to do this, so there is a specific tutorial for that bundle assignment maps. I'll provide the links here where you can go. And in this example, we are using arcade fasciculus, and then we create the assignment maps. We create 100 assignment segments, so it's totally up to user. If you would like to have just 20 segments, you just provide 20 here. And then we also have some interactive visualization, so when you run this tutorial you can see that. Now if you are interested in bundle shape similarity and you don't want to do bundle shape similarity for many subjects, you just want to do it for 2 subjects for example, or even if you have extracted a bundle from Recobundle and you want to see how good Recobundle did, so what you can do is you can have model bundle and the extracted bundle, and then find shape similarity score for those 2. It can kind of validate that how well the method is performing, how well the extraction was. Or for example, you are doing a streamlined registration and you want to see before and after how good the results are. You can again do bundle shape similarity for those 2 bundles. So if you want to do just for 1 or 2 bundles, here is the tutorial for bundle shape similarity in Dipy. Here it shows you how you can have 2 bundles. In this case we have Singulum, and then we are showing the bundle shape similarity score between those 2. So you can follow this tutorial in this is a Pythonic tutorial. If you like to have your own script in Python and you would like to do that, let's go back to here. So we are at 48. So I just want to mention the data we have here. We have a very rich representation of data. We have many points on streamlines, and we're using all the streamlines and all the points. That's why it may be taking a bit of time, but it's a lot of data to process. And in meantime, if you have any questions, ask us on Gitter, or for the workshop there are chats. You can ask in analytics chat if you have any question, or if you would like to run this BUAN tutorial on your own data, then reach out to me if you have any questions. And you will need to have this kind of structure for your data. The bundles that we are already providing with BUAN, 30 bundles, or you can even go up to 80 bundles. We have both atlases that are in MNI space actually provided here. And if you have your own atlas, you would like to use that, so instead of using this atlas that we are providing, you can use your own atlas. It could be in MNI space or in any other space. You can download it here. It's linked here. And if you want to run this on an animal data, you can also run BUAN as it is. Just provide your own atlas. And then you will need to have your data in this structure. You can give this name any name you want, and then you have control and inside this the name of folder, or this could be any name, but these inside these anatomical org bundles, rec bundle, they should have this name. The folder name should be this, but inside it you can have as many anatomical measures with whatever name, and also the streamlines, tracks, as many as you have in any name it could have. It should have some name that corresponds to the rec bundles and org bundles. Or for example, you have AF labet like this, it should be same in all the subjects. It should be the same name. So the output of linear mixed models will give you saved p-values per segment, and also it will be a numpy file, and also the minus log p-values file. And if you want to create your own plot or do something with those values, you can do later. And it by default saves this kind of a plot as shown here with two horizontal lines for p-value less than 0.01 and 0.001. Great, this is done. Let's see. So as I was saying, it created a plot and saved the p-values. So let's see. This is the plot. It looks very much the same as we have in the tutorial. So here we can see some group differences around 50. And some may be here. So this really depends on at what level of significance you want to see. So if you are interested in looking at p-value less than 0.01, anything here or here. Now if we want to see what exact location on the bundle that area is located, so as we have in the paper, here we have, it's a we have the functionality here. Let's see how we can do with dipy horizon. Maybe you have already used it in earlier sessions. So all we need to do is write dipy horizon, and then we give it the model bundle for which we want to see where the differences are. Or you can give it any bundle, but let's give it a model bundle. Should be arcade fasciculus in this case. And then from the linear mixed models output, we will use the p-values that we just saved, not the log of, but the p-values. And this is a flag BUAN that we want to give this to tell it that this is for the BUAN. And then the BUAN threshold is where you want to locate, or which area do you want to signify where the p-value is less than. By default it will be 0.05, but let's say we want to see 0.001. So it will highlight the area. By default it will highlight in red color, but we can also change the color if we want, wherever the p-value is less than 0.01. We do not have any p-value less than 0.001, so that's why it hasn't highlighted anything here. Let's give it 0.05 and we'll highlight the area wherever p-value is less than 0.05. Here we can see all these locations, all these segments. So it will also make some combined segments. So these are the areas where p-value was less than 0.05. Let's select 0.01 as we saw here in our plot, the red line. So this will highlight less areas as compared to 0.05. Yes, here we can see. So by default it will highlight in red color, but if you would like to change the color, you can actually do so. All you need to do is add another flag, BUAN highlight, and then you give it 3 colors, RGB, 3 colors. So here 1, 1, 0. This will create yellow color. Or you can add any color you want. So the color of bundle will remain the same color that we have from the tractography, and then the highlighted color you can specify and create figures for your papers. Now let's go to the second part, which is bundle shape similarity of a specific bundles across populations. So let's create a folder again, SM plots, and now we have 10 subjects and 10 subjects have arcade fasciculus, and this will bundles in common space. So the workflow is called Dipy BUAN shapes, and then we give it the subjects folder where we have all the subjects, and then we give it output directory name, and then it will run shape similarity workflow. So this workflow will generate, in our case we have just one bundle, so one plot, but if you have, for example, 30, it will create 30 plots. And so the shape similarity score varies from 0 to 1, where 1 being the highest similarity and 0 being the lowest. So by default it uses this color scheme from 0 to 1, from white to blue. So if you ever see light color, it means less shape similarity, and if it's darker, it means higher shape similarity. So this will actually calculate shape similarity of each bundle with every other bundle. So for example, for this row, this is zeroth subject, let's say first subject with itself. So in the diagonal we will always have dark R1, and then with the second subject, third, fourth, fifth, 5. So in one row you can see that how it is doing, how similar it is across the subjects. So here first 5 subjects are from control and last 5 are from patients. And as I explained earlier, there is this tutorial. For example, you don't want to create these metrics, but you just want to look at 2 bundles, then you can follow this tutorial. So this is a fully connected graph or network, and yeah. And here is linked to all the 64 subjects. If you would like to replicate the figures and results that we have in BUAN paper, you can do that. This will save a plot that will look something like this, but this is for Uncinet, but right now we're running it on arcade fasciculus, so we'll have one for that. And it will also save a numpy file that will be a matrix that will have these values, similarity score saved in it. So for example, you want to load it and maybe visualize it in different way in your Python notebook, or if you want to do any clustering on this data, you can do that because it saves that data as a numpy file. Great, so this is finished. Let's see in the plots. As I said, we have a numpy file and then we have a plot saved. So let's see. Here it looks like this. Pretty good. And yeah, by default it uses 5 or maybe 6. Let's check it, what it uses by default, the threshold for shape similarity. You can also change it from the workflow. I'll show you quickly that too. So here we can see that this is actually, this dataset looks good. Here we have very dark plot, dark matrix, which shows that we have a good shape similarity among all the subjects. let me show you one more thing. So if you want to see what are the available parameters or options that you can have, what are the arguments and flags, you can always do -h. That will show you all the options and a description about all the arguments in Dipy workflows. So here you have. These are the ones that it takes. And then here you have positional arguments that are necessary, and then these are the optional ones. And then it tells you here threshold, you can change the threshold. For example, you want it to be, I don't know, 2, 15, so it's up to you. And force is when you want to, when you already have some plot saved with same name and you want to overwrite it. And you can do same for linear mixed models workflow, or actually any workflow in the Dipy. And so -h for help. So here it shows you if you have different number of disks, different number of segments you want to use, and then the output, the positional arguments, and etc. So I'll stop it here, and if you have any questions, reach out to me, reach out to us on Gitter. If you have your own data and you would like to run this, and you have any questions, feel free to reach out. And I hope you enjoyed this session. Thank you.